Good morning, everyone.
Good morning.
My name is Vineyard, and I'm going to be giving you a brief presentation on monitors today. Can anyone tell me how many different types of monitors there are?
Four.
Can you name them?
CRT, LCD, plasma, LED.
All right. Gets us off to a good start anyway. Okay. Originally, computer monitors were used for data processing only, and television receivers were used for entertainment. The first computer monitors used cathode ray tubes, or CTRs. Prior to the advent of the home computers in the late 1970s, it was common for computers to be called video display terminals, and with the integrated keyboard and other components of the system and a large chassis. And the display was monochrome and far less sharp and detailed than on the modern flat panel monitors. Some of the earliest home computers, such as the TRS-80 and the Commodore 64, were limited to monochrome displays, but display's capability was already a standard feature in the Apple II, introduced in 1977. The Atari came out in 1979. Either computer could be connected to a TV through an antenna terminal used for the purpose to make a CRT color monitor for the optimal resolution and color quality. By the end of the 1980s, color monitors were clearly displayed at a 1024 by 768 pixels and were widely available and increasingly affordable. CRT technology remained dominant in the PC market into the new millennium. Partially because of the cheaper production and by the wider viewing angle of 180 degrees. A CRT monitor contains millions of tiny red and green and blue phosphorus dots that glow when they are struck by an electron beam that travels across the screen to create a visible image. I've got a couple little videos here to show you.
Inside every TV set, there's a big tube. You call it a picture tube, but the correct name is cathode ray tube. It takes the waves from the transmitter and turns them back into electrons. In the back of this tube, there's an electron gun which shoots the electrons at the front of the tube. The front of the tube is coated with a special chemical which lights up when the electrons hit it. And this is what makes the picture.
I get it. The Oerlikon tube turns the picture into electrons, and the cathode ray tube turns the electrons back into the picture.
Precisely, Michael.
That's a cute little video that I found that I wanted to show you all. I showed it to my wife last night. She loves cartoons, so it's just right down her alley.
Monitor work. Signals from your computer's video card are loaded into 3 electron guns at the base of the monitor. There is one gun for each of 3 colors: red, blue, and green. These 3 colors, when mixed together, can create all the colors you see on your screen. Now, these guns don't shoot bullets. Instead, they shoot a powerful beam of electrons towards the face of the monitor. The beams pass through the deflection yoke. It uses magnetism to bend the electronic beams so they can sweep across the entire screen and create the picture we see.
What happens once the beams have swept your monitor? Special chemical phosphors are painted on the inside of the monitor. Energy from the electron beams makes the individual phosphors glow either red, blue, or green, depending on the type of phosphor. The stronger the electron beam, the brighter the phosphors glow. A sheet of metal with holes in it helps keep the electron beams aligned exactly with the phosphors. This is called a shadow mask. The beams sweep across the entire screen 60 times per second. It happens so quickly that you are unaware of the firing process. Instead, your screen appears to be a steady, continuous image, just as it does now.
Okay, I brought an example of the CRT monitor with me today, and I already discharged it and taken the case off. So if y'all want to, after it's over with, you're more than welcome to take a look at it. And don't be too worried about damaging it, because I dug it out of the building, so you will notice there's some rust and dust and corrosion and everything else in there. Now, in 1981, IBM introduced the first color graphics adapter, which was capable of rendering four colors at a maximum resolution of 320 pixels horizontally by 200 pixels vertically. And in 1984, IBM introduced the enhanced graphics adapter, which allowed for 640 pixels by 350 pixels, and with 16 different colors. And in 1987, IBM introduced what we all know as the VGA array, or the video graphics array, which is used in most computer monitors and even TV monitors up until the flat screen panels come out. And actually, we still use the VGA array pins to hook our cables to the monitors in most situations. And in 1990, IBM came out with an extended graphics array that allowed for 800 by 600 pixels, the true resolution colors with up to 16.8 million colors, and 10,024 by 768 pixels with availability of 65,536 different colors. Now the LCD, I've got that marked as LCD, LED, because basically they're both on the same form factor. The only difference is the light emissions, which I'll go into a little more depth momentarily. LCD display stands for liquid crystal display, and it's a flat panel display, electronic visual display, video display, and they use a light moderating properties of liquid crystals. Liquid crystals were first discovered in 1888 by Frederick Ratzinger, and in 1972, the first active matrix liquid crystal panel was produced in the United States by the Westinghouse in Pennsylvania. In 1983, researchers from the BBC in Switzerland invented the super twisted pneumatic structure for passive matrix address LCDs. In 1996, Samsung developed a pattern technique of multiple domain and plane switching, subsequently remained the dominant LCD design of today. LCDs are used in wide range, such as I've stated before, as in television monitors, instrument panels. Your smartphones have LCD displays in them, or LED. Your aircraft cockpit displays, and a lot of signage. LCD is more efficient and can be disposed of more safely than the CRT monitor because of the lower power consumption and that it uses batteries powered to the electronic equipment. In 2008, sales of TVs with LCD screens exceeded CRTs for the first time in the world. The LCD panel is lit by two cold cathode fluorescent tubes placed on the opposite sides of the display and an array of panel of CCFLs behind the larger display. A diffuser then spreads the light evenly across the whole display, while CFLs are less efficient than LEDs and require somewhat more costly inverters to convert your DC power, your AC power to DC power, then back to AC in order to light the fluorescent tubes. The LCD panel is also lit by LEDs at one or more of the edges of the screen, or can be used in a light array panel behind the entire display. There are three types of LEDs in use today: edge-lit LEDs, backlit LEDs, and local dynamic backlight. The local dynamic backlight controls individuals or in clusters to control the light and color intensity at any given part of the screen. Now, there are 6 parts to an LCD or LED screen. Does anyone knows what those 6 parts are or what they do? Well, your first layer in the LCD screen is a vertical filter film, and it polarizes the light as it enters. The second layer is a glass substrate with electrodes, and shapes of these electrodes will determine the dark shapes that will appear when the LCD is turned on. Vertical ridges are etched on the surface of liquid crystals are in line with the polarized light. Excuse me. The third level is a twisted pneumatic liquid crystals, which I mentioned earlier that was designed by IBM. The fourth layer is another glass substrate with common electrode film, but it controls the horizontal ridges to line up with the horizontal filter. Fifth layer is your horizontal filter. It films to block or allow the light through. And your last level is a reflective surface to send the light back to the viewer. The advantages of LCDs or LEDs are the low power consumptions, depending on the set, display of the brightness, and the content. They typically use 30% to 50% less power than CRTs, and LEDs normally use 10 to 20% of the power of a CRT. It's very thin, and therefore it's easier to set up. You don't have to have it 18 inches from the wall where it sticks out so far in the back. You can be flush mounted, it can be made in almost any size or shape, and theoretically there is no resolution limit. Now, some of the disadvantages are the uneven backlighting, which is normally caused by the older monitors, dead or stuck pixels, which can occur during the manufacturing process or in your home use. If somebody touches a screen or something, it can kill the pixels if too much pressure is applied. Another disadvantage is loss of brightness and much slower response time in low temperatures. In some sub-zero environments, LCD screens must have an exterior heating element in order for the display to work. Now we'll move on to the plasma display, which also is a monochrome plasma display. It was invented in 1964 at the University of Illinois. The original neon orange monochrome display panels built by glass producer Owens Corning in 1970 were rugged and had neither memory nor circuitry to refresh the image. A long period of sales declined through the late 1970s because the LEDs were $25,000 more than the same size CRT. And in 1982, Fuji introduced the world's first 21-inch full-color display. And in 1985, they introduced a 42-inch plasma display that had an 852 by 480 display with the same resolution, and the only plasma display to be retailed in 4 Sears stores in the United States. There was only 4 stores that were Sears that even you could go and see the end result of the plasma displays. And they were priced at $14,999. A little bit expensive today. In 2010, the Consumers Electronics Show in Las Vegas, Panasonic introduced a 152-inch, 2,160 plasma display, with 3D graphics. They shipped 19.1 million TVs, plasma TVs, in the late 2013. Now, a little odd note that I found, Panasonic announced at the end of 2013 that as of March of this year, they would no longer be making plasma displays. So Panasonic's dropped out of the race. Does anybody know how many different manufacturers of plasma displays there are? Right now in the world, there's only 5 left. That's it. If you want a plasma, you've got to go to one of these 5 companies. And that is NEC, Fuji, Pioneer, Samsung, or LG. Now to get a little more into the plasma works basically the same way as the others do. But typically the light passes through millions of tiny cells like they do in others, and there are called cells or bulbs with a mixture of noble gases, and they reach temperatures up to 1200 degrees Celsius. So your plasma springs do get extremely warm. The photons in the stream vaporizes the noble gases and causes the phosphorus to strike the painted surfaces inside the cell. And when this phosphorus strikes the molecules, it what produces the flash and gives you the color range. In color panels on the back side of each cell is coated with the phosphorus, as I stated, and the ultraviolet photons emitted by the plasma excite these photons, which give off visible light with colors determined by the photon material in aspect of our red, blue, and green. Now I'll move on to the OLED, which is basically the same principles as all the rest of them. The only thing we keep doing is advancing in our technology and making things quicker, brighter. We're following Moore's law. An image on a high-definition television is 80 inches wide and less than, or imagine having a high-definition television that's 80 inches wide, less than a 1/4 inch thick, and consumes less power than most TVs on the market today. Imagine being able to roll it up, and use it when you need, to unroll the display in the car, and to be able to unroll the display anywhere that you needed to use it. The display itself is a thin, OLEDs are solid-state devices composed of thin films of organic molecules that create light with the application of electricity. OLEDs can provide a brighter, crisper displays on electronic devices that use less power than conventional light-emitting diodes or liquid crystal displays used today. An LED or an OLED is a solid state, as I said, and it has 100 to 500 nanometers thick. That's about 200 times smaller than a human hair. So we're getting very, very thin with these. They can either have 2 or 3 layers of organic material to help transport the electrons from the cathode to the emissions layer. I've got one other video I want to show you on these. Bear with me a moment.
What we just observed was the electron injection into an organic matter. Now that's a fancy way of simply saying, if I go ahead and inject some charge on one end and some opposite charge on the other end, they can meet in the middle and excite a molecule. That molecule will glow, especially if you have still a lot of sodium that you're seeing right here. So the consequence is that given any material, I can electrically excite it. Often things are not very, very efficient in the way they glow, and hence we don't necessarily observe it. Here, we're passing a lot of current through a very small amount of material. Even if it's not very efficient in glowing, it's going to still be observed because we're just doing this so repeatedly over and over and over and over. So by no means is this a very efficient LED that you observe, but the essence of it is very similar to what happens in these very slick-looking displays. This is an organic light-emitting display. It uses organic light-emitting devices, which essentially are thin layers of molecules. And you're looking at a series of them, the ones that emit red, green, and blue side by side to generate these full-color images you're observing here. But what you're really looking at is thin films, 100 molecules thick, that have two electrodes, one on the top, one on the bottom, you apply about 5 volts between top and bottom, and current will flow through those molecules. As the molecule passes current, if a positive and negative charge arrive on the same molecule, they form an excited state of the molecule. That molecule can then relax by dropping the negative charge into the positive charge. In the process of that relaxation, give off a photon. Very much the same as what's happening at Bitcoin. The only thing you need to do next is make sure that you have 1 million individual little devices side by side, so that each one can glow of different color and each one can glow at precisely right point to generate the image. So I'm going to advertise this technology just by a little bit. This is a much simpler technology than you compare to LCD technology. LCD technology has polarizers, crystals, electrodes, color filters. None of that is present in this particular OLED technology. OLEDs simply have these molecules between the electrodes. Hence the manufacturing of them should be much, much simpler as time goes on. I say as time goes on, because it's a very new technology. There are a couple of technological scaling up challenges that still need to overcome. The actual display is 0.3 microns. Just to give you a scale, your hair is 15 microns in diameter. So this is on the order of 1/100th of the thickness of your hair. If I have a film like that, I do not need very thick substrate to grow it on. Indeed, this whole device is only 3 millimeters in thickness. The power consumption of these displays is about 1/2 of the power consumption of similarly sized LCD. Beyond that, this is the very first generation of technology. It's using technology that was invented maybe 10 years ago. Stuff that has been invented more recently is another factor of 10 more efficient. So in the long run, we can see that these particular displays should be about 10, 20 times more efficient than the best LCDs of today.
Okay, that brief little video gives you a little more in-depth into the OLEDs. Would anybody like to take a guess on how many layers there are to the screen on an OLED?
5.
6. Just the same as the LCD or the LED. And actually, they're exactly the same layer levels. You have the substrate, the anode layer, which is your transparent layer, the organic layer, the conducting layer, and the emissive layer, and the cathode. Now, I just mentioned cathode and anode. Do anybody know what synonyms for these two words are? We hear cathode and anode all the time in electronics. All it boils down to is they're positive and negative. An anode is the positive side and the cathode is the negative. Now, on the OLED, the advantages of the OLEDs are brighter. The plastic layers of the OLED are thinner and lighter and more flexible than the crystal or the glass used in LCDs and LEDs. They do not require backlighting like the LCDs or LED does. And they have a large field of view. They come close to a CRT monitor at 170 degrees. Now, the problems with the OLEDs is the lifetime. The red and green have a sustained life, but the blue they're having trouble out of because it decomposes so quickly. At the max right now, they're only saying that it'll hold up to about 1,400 hours. So it's not very long on that. In normal consumption, I think it works out something like about 8 years or so. So it's not something that's going to die on you as soon as you buy it. Now, the manufacturing processes are quite expensive right now. They've not been able to go in through and get all of the technology in order to blend everything together to bring the price down yet. And water can be a major distractor. In a high humidity area, it can cause problems inside the case because of the moisture buildup. So they're having issues with being able to seal the cases off enough and still allow an airflow to keep everything cool. And that's about all I have for y'all today. If you have any questions, like I said, I do have 2 different types of monitors sitting down here if you'd like to take a look at them or ask any questions about it. I can tell you how to discharge the no CRT if you'd like. Does anyone have any questions? Thank you very much.